So in the last video, we talked about density-independent growth. Now, a lot of times students will look at the density-independent growth model and they'll say, well, this is highly unrealistic. It never happens in nature. And I did mention some cases where it does, right? So if you have invasive species in particular, we often see this kind of exponential growth. Another example I wanted to show you is this predator removal. So when predators are removed from an herbivore population, what you'll tend to see is that the population will begin to grow exponentially. Now, this is assuming that that population was regulated by its predator. So as it's growing exponentially, there will come a time when the environment can no longer hold the number of individuals. And in fact, usually what happens is, in this case, that the population has overshot the environment. What you usually see is a population crash here. Oh, I'm sorry. So a population crash right here. And some people will say, well, that's density-dependent growth, but it's not. So density-independent growth follows this classic shape it's the exponential growth curve. And what's limiting the population in this portion is actually its ability to reproduce. It's not being limited by its environment, only up here. Whereas in classic density-dependent growth, those limitations occur all throughout the growth curve, or through most of the growth curve. I also want to mention that these are mathematical models. And we as scientists make mathematical models to mimic the real world. And so we'll take a situation that we see in the real world and we'll mimic it through a model. Now, if it's a mathematical model, we can take things out, we can put things in, we can tweak it, and we can look at ways different things affect the model. It helps us better understand the underlying ways that this phenomena acts. So again, we looked at density-independent growth before. This is the whooping crane example that I had given you. Whooping cranes, their populations had declined because of habitat loss. And now you'll see, and humans were competing against them for food. And once they started to become protected, you can see right here that their population grew. Now again, there's going to come a point where they're going to be stopped. But at this point, we were looking at exponential growth. The other kind of population growth is when populations grow dependent on their density, or density-dependent growth. Here seen in the barnacle, we usually see these as classical S-shaped curves. So density-dependent growth is also called logistic growth. And this is where the growth of the population is affected by the density of the population. And remember, populations can increase by adding individuals through birth. They can decrease by taking individuals away through death. So as populations grow bigger under this scenario, the birth rate decreases, the death rate increases, or both happen. This is usually caused by competition for resources. It can be caused by disease and predation, but I usually think it's only caused by competition of resources, or for the most part. So again, this type of growth is called logistic. It has this classic S shape. So in the other one where I showed you the herbivore dynamics, you can see that at some point it just kept growing exponentially and then crashed. In this case, you can see there's definitely an influence of the resource on the entire population. So where do you think competition for resources is most intense along this curve? Well, oftentimes students get very confused by graphs. You can see up here, the population is no longer growing. This actually is the place where competition is most intense. And that's because at this spot, you have the maximum number of individuals that that environment can support. And once you get to that part, you have the most individuals that you're going to get competing for limited resources, so competition will be most intense. Logistic growth introduces us to the concept of carrying capacity. We use the letter K to indicate carrying capacity. The letter C was already being used in the model, earlier in the model. So carrying capacity is the maximum population size that a given environment can support. And you can see right here when the population is low, there's a lot of extra space between where the population is and the carrying capacity. As this population grows towards the carrying capacity, that space gets less and less and less until we get close to the carrying capacity, and then the population does not exceed it. So what factors might influence how high a carrying capacity is? Can you think of a way to increase or decrease the carrying capacity of an environment? These are questions you might see on the written portion of your next exam. And so to think about it, carrying capacity is all about resources. You can increase the resources, you increase the carrying capacity. You decrease the resources, you decrease the carrying capacity. Factors that affect the amount of resources are going to be factors that influence the carrying capacity. So was Thomas Malthus right? Remember we had talked about the Malthusian trap earlier in this lesson. Thomas Malthus had observed that humans follow an exponential growth. And he also observed that food production was a linear function. Now that was true in his time. So what happened was you would just increase the number of land in production, in agricultural production, and you would increase the amount of food. So that was before the Green Revolution, before the Agricultural Revolution. And so you're going to see this linear growth. So was he right? Well, no. Our food production actually started to increase exponentially as well. But here you can see he predicted that here you'd get into the trap, which is when food required would exceed food produced, and we would say widespread misery and starvation and disease. And this was his writing actually, remember this is 1700s, his writing was very influential on Charles Darwin when Darwin was coming up with his theory of natural selection. So maximum yield is a really important concept when we talk about logistic growth. So at what point do you think on this curve is the population growing the fastest? That means when you have the maximum number of births and the minimum number of deaths. Well, we can look at it this way. When you get to halfway to the carrying capacity, you actually are growing the fastest. So let's slow down a bit and let's look at right here in the beginning part of the curve. This way the rate accelerates. So here you're getting a faster population growth. It actually looks a lot like logistic growth. And that makes sense because there's so much room up here that individuals aren't competing very much. Once you get to this point, we call it the inflection point. It's at half of the carrying capacity. All of a sudden you get what we call inflection, where the curve changes shape. And it's at this point where we have the maximum growth. It's the maximum birth rates, the minimum death rates. We have the maximum replacement rate because if we're purely exponential, you're at the top of your curve right here. Now at this point, all of a sudden, the effects of resource limitation are being felt. The birth rate is decreasing, the death rate is increasing, and so the rate of growth slows down. So now we have crowding, and it's going to continue to slow down until it gets to the carrying capacity. Now this point of maximum growth is actually a really important point in conservation biology. It's actually used to calculate sustainable yield. So if you have, say, a fishery, and you want to know how many fish can you take in any particular year, what you're going to look at is the carrying capacity and go in half, and that's the number that you can take back. So it's maximum replacement rate at that point. So optimum yield or maximum yield occurs when the population growth rate is at its peak. It occurs at half of the carrying capacity. Oh, we're not going to discuss with the person across from you, but I want you to look at this and what are some of the reasons why a population growth would look like this. So again, students often say it's not realistic. It's not like the population gets to the carrying capacity and then it absolutely stops. What happens is the population overshoots and it undershoots. So as it gets above the carrying capacity, more individuals die than are born. And then it'll undershoot and more individuals will be born than die. And so it'll hover around this carrying capacity. Sometimes you'll get a really tight hovering. And sometimes you'll get a very long sequence here. And what really is happening is it has to do with the life history of the organism, how fast they can reproduce. And this one, I would imagine, it's a very slow reproducing organism with a large lifespan. And so it takes a while for the population to catch up to the carrying capacity, whereas this is a much quicker growth. So density-dependent growth. So the population growth is under limited resources. Competition for resources slows growth. Again, we're going to look at the barnacle, where you get this rapid increase, and then it's going to level off. Your birth rates are going to decrease, your death rates are going to increase. here's where you're going to find, the carrying capacity. That didn't turn out so well. So here's you're going to find the carrying capacity. There you go. That was a little funky, but here you can see carrying capacity right there. Humans, or world population growth, follows what we think of as an exponential growth. This graph is old now, but it has a lot in it I like. So if you look at this, we are now past 7 billion, just so you know. We reached it a few years ago. So if you take all of human history, it took for it to reach 1 billion, it took all of human history up until right around here to reach 1 billion people. We reached 2 billion people only 100 years later. The third billion was added in just 30 years, the fourth in 15. It's because our doubling time, right? It's lessening because our population numbers are getting bigger and bigger and bigger. And then if you look at 6 billion, it was right around 2000. We were at 6 billion. And it was only like another 10 years before we're at 7 billion. And so exponential growth can be quite rapid and can be explosive. And in some reports, there are some papers that will say that human population growth exceeds exponential growth and that human population growth actually is starting to slow down.